Okay, so now that we've looked at the context of addition and subtraction, we've also looked at the actual strategies for adding and subtracting and evaluating expressions. Now let's look at fractions. So why do we add and subtract fractions the way we do? So for example, if we have 1/5 plus 3/5, what we generally say is, since the denominators are the same, we add the numerators, keep the denominator the same, and have our result as 4/5. Now, that is the rule. That's the leap of faith here. But why does it make sense? Why does it make sense with our definition of fraction? So let's go to a manipulative and see if we can add 1/5 plus 3/5. So I'm going to be using Cuisinart rod, but in a way that represents our fractions. So for example, if this is 1, then I can see that this is 1/5, right? Because you can see that it takes 5 of them to fill the whole. So it takes 5 of these to fill the whole. So if that's the case, then that's 1/5. And 3/5 would then be 3 of them. So that's 3/5. And if I added 1/5 and 3/5, I would get 1/5 plus 3/5 would be this much, and which is 4/5. It's less than 1. It is 4/5. So if we're looking at our definition of fractions, where we're taking a length and another length, and we're adding them together, then our resulting length is going to be 4/5, the sum of those two. Now, it makes sense that if you're adding fifths and one on top of one together with other fifths, we're still going to be counting fifths. If each one of these little squares is a fifth, then no matter how many of them we string together, there's still going to be that many fifths. The nature of the square is not going to change because our whole is going to remain the same. So let's take a look at this Patty's thinking. Patty says that this is 1/5 and this is 3/5, and if I add them, I get this this picture, which 4 of the 10 are shaded. So 4/10 are now is the sum of 1/5 and 3/5. And the way she did that, she writes it out in a number sentence. So she says 1/5 plus 3/5 is 1 plus 3 over 5 plus 5 is 4/10. Well, clearly we know that this is where the issue is. We don't add the denominator, but why not? What is the problem here? Pause and think a little bit about why is this not making sense with addition of fractions. Now, the issue is that we are representing fractions in this way. Right? So this is 1/5. We're drawing the whole and the fifth. And 3/5, we're drawing the whole and 3/5. This is the way we normally use draw these fractions when we're separating the whole into 5 equal parts and shading 3 of them. So look, this Patty's answer, when she puts those two together, is quite meaningful. And in fact, the 4/10 is a quite meaningful interpretation of that shading. Every step here makes sense, except for the fact that we're working with the wrong picture representation. Let's go back to our picture here. So what Patty saw is that we had 1/5 and 3/5. She saw this whole thing as representing 1/5 and 3/5. So when she added them together. she added them together to get 4/10. It made perfect sense to her. The problem is we don't add the wholes. The wholes here are not part of, these yellow rectangles are not actually part of 1/5. 1/5 is just this. So when we're adding 1/5 and 3/5, we don't need to bring the wholes with us. We don't double the amount of whole. We just add those values the way we did up above, the way we did here. Yeah, the whole remains the same. That's our ruler. That's our measuring stick. That's how we say, well, all right, we have this amount. How many of those do we need to fill the hole, and how many do we have? But the hole itself is not part of our definition of the length that we're looking at. So Patty is confused because we're looking at a picture that might seem easier, but it actually complicates our understanding of fractions. And that is why from the very beginning, I've really emphasized us shying away from saying 1/5 means we split the whole up into fifths and then we shade one of them. That is where the issue starts, is that representation of a whole, of a fifth. So instead, we were focusing on that one thing, that one piece that we need 5 of to fill the whole. That's our 1/5. It doesn't matter how the rest of the whole looks, but we need 5 of those to make a whole. So take a look, take a little bit of time, and see if you can figure out questions B and C, so that using the representation of fractions that we have worked on, and using our definition of fractions. All right, now let's take a look at this problem. So if we have a number of strips, and let's say one whole, and that whole can be, we can look at halves, we can split it up into halves, or we can split it up into thirds. And what we need to do is we need to look at seeing how we can possibly figure out where how we can calculate the values here. 1/2 plus a third, 2/3 minus a half, and 2/3 plus a half. So let's see if we can do that on our Cuisinart rods. I'm going to clear this. There we go. So we had 1/2 plus a third. So I'm going to take this as the whole, and these are as halves, and these are as thirds. That looks very similar to what we were looking at. So this is the whole, 1/2 and 1/2. It takes 2 of those to fill the hole, and it takes 3 of the red ones to fill the hole. And I need to figure out what 1/2 plus a third is. So what is 1/2 plus a third? Now, the 1/2 plus a third is this amount. Well, is it less than 1 or greater than 1? We know that the whole is this piece, so it's less than 1. So it's going to be less than 1. This is 1/2 plus a third. Now, how could I possibly figure out how much all of that is? Because I have this missing piece, and that missing piece I don't even know how to express. But I could see that I could look at these gray pieces. I could split 1/2 into 3 pieces and the third into 2 pieces, and actually start looking at these pieces, which are 6, because I need 6 of them to fill the hole, and see, hey, maybe I can use those to show my distance here, my sum. So let's see, if I have sixths, would I be able to split to see how many sixths I've got? I would. If each one of them is a sixth, then I actually have 5 of those sixths. Do you see that what we did was we were adding different fractions? We did not bring the whole with us, but we needed to find a different way, a different unit, to be able to figure out how much the sum is, the sum of a half and a third. So this was 1/2 plus 1/3. Let's look at the next question. The next question is 2/3 minus 1/2. Let's do that. 2/3 minus 1/2. The thirds were red and minus 1/2. So 1/3 and 1/3 minus 1/2. So we're looking for this. Well, it should look very familiar because that difference, that single unit, is you need 6 of those to fill the hole. So that is actually 1/6 if we split the whole into different ways, and if we are using the 1 square as our counting unit, because we know 6 of those are needed to fill the hole. And what's the last question? 2/3 plus 1/2. 2/3 plus 1/2. All right, let's do 2/3 plus 1/2. 1/3, 1/3, 1/2. Now, is that going to be less than 1 or more than 1? That actually looks like it'll be more than 1. Interesting. It's going to be more than 1. This is 1. Well, how much more than 1 is it? It's one of those singles, more than 1. And that's a 1/6. So the solution will be 1 and 1/6. Or how many sixths? Well, there's 6 sixths in 1, because it takes 6 of them to fill the hole. So it's 7/6. All right. So you can do the same thing by folding. So instead of looking at the rods, you can fold a piece of paper in different ways to be able to figure out or to model addition and subtraction of fractions.